All right. Going to run through section 9.2 real quick. So this is all about arithmetic sequences, which is one of our new vocab words for the day. Our EQ is what are arithmetic, spelled the same as arithmetic, but we pronounce it arithmetic. What are arithmetic sequences, and how can I write both explicit and recursive formulas for them? So in 9.1, we did explicit and recursive formulas, and today we're focusing on the same thing, just for a certain type of sequence, basically. So as a warm-up, you want to run a 10K race 12 weeks from now. To train, you're going to run 4 times per week at a fixed distance. Each run during week 1. So during that first week of training, you're running 3 kilometers. By week 11, you want to run, each run will be 9 kilometers. Okay, so each week we're going to progressively add more distance on to that. The question is, how much distance are you adding on each week? So if we think about this, like in week 1, we are running 3 kilometers each. And by the time we fast forward to week 11, we are running 9 kilometers each run. So we can kind of treat this like slope from back when. So if you think about how much is that distance changing over that time, we're running from 3 kilometers per run to 9. So that is an increase of 6 kilometers. And that increase is happening over a 10-week time span, because 11 minus 1 is 10. So we're basically treating it like slope, the y2 minus y1 over x2 minus x1. And then this is going to equal 6 divided by 10, or 0.6 kilometers you are adding on per week. Okay, so every week it's increasing by 0.6 kilometers, which means that, let's say in week, so we could make a table for this that says how long will each run be during week 8. So if we think about like week 1, this is our week, this is our distance. During week 1, it was 3 kilometers each. And then our pattern is just going to be adding on 0.6 kilometers every week. And there's a lot of different ways you could get to this mathematically. Here we're going to go with in week 2 that we're adding 0.6. So this would be 3.6, then 4.2. Again, just adding 0.6 every time. 4.8, 5.4, 6 kilometers even. Then we have 6.6, and finally in week 8 would be 7.2. So 7.2 kilometers during week 8. During week 8. Okay. So there are a couple different ways to go about solving that. You could also do some multiplication to cut down on the time that it takes to solve that problem. But that is one way to solve that, and kind of what we're going to be getting into today. Okay, so the one definition for the day is what is an arithmetic sequence. Actually, there's 2 definitions within this one thing. An arithmetic sequence is defined as a sequence that has a constant difference between terms. That constant difference basically means if you take any term and subtract the previous term, you'll get the same thing every time. Or to say it even in a more simplistic way, that's like the mathy term, is that the sequence has a constant difference. It basically means the pattern must be adding or subtracting as you go. And it has to be the same every time. So it can't just be like, I'm adding 1, then I add 2, then I add 3, then I add 4. Like there's a pattern there, but in order to be arithmetic, it has to be adding the same thing every time. So the first question is like, is this arithmetic? If I look at this first sequence, am I adding the same amount to get from one to the other? Well, from 5 to 6 is plus 1. Oh boy. Plus 1. From 6 to 8 is plus 2. So automatically, like I don't even care what the rest of the pattern is. This is not arithmetic, because it would have to be like, if the first difference is plus 1, then it has to continue being plus 1 over and over again. So this would be not arithmetic. There actually is a pattern there, but We're not going to put a name to that type of sequence. This next one, 6, 10, 14, 18, 22. 6 to 10, that's adding by 4. 10 to 14 is adding by 4. 14 to 18 is adding by 4. And sure enough, we see that this is this is consistent. This is adding the same amount every time. So we would say this is arithmetic. And we use the letter D to stand for the common difference. So we would say the common difference is positive 4. Okay. So when we talk arithmetic, if it is arithmetic, go ahead and say what is that constant difference. This third sequence from 23 to 18 is subtracting by 5. 18 to 13 is subtracting by 5. 13 to 8 is subtracting. So we see that sure enough, this is subtracting 5 every time. This is indeed arithmetic. And the value of the constant difference is going to be that pattern of negative 5. Okay. And then 50 to 25, that's subtracting by 25. 25 to 12 and a half is not subtracting 25, so it doesn't even matter what happens here. This is actually not arithmetic. So for today, it doesn't matter. We're actually going to talk about sequences like this tomorrow, where it's 50 to 25 to 12 and a half. And what you might see is that the pattern is it's cutting the number in half every time. And that's called a geometric sequence. And that's the topic of 9.3. But for this lesson and our purposes, we're just going to leave it alone. Okay, so in 9.1, we talked about two different types of formulas. There's recursive and then there's explicit. So if I were to write a recursive formula for this sequence from 23 to 18, the first thing, if it's recursive, I'm going to say right away what the first term is. I need to know the starting point. So a sub 1 is 23, meaning the first term in my sequence is 23. And then every recursive formula will always start the same way. Okay, like not every one forever, but every recursive formula you are going to write will start the same way. Okay, in order to get a certain term, you're going to take the previous term and do what to it. So this is like saying, how do I get the second term from the first term? Well, if you look, this is like saying from 18, or sorry, how do I get 18, which is my second term, from 23? Well, we saw that the pattern was to subtract 5 every time. So all I have to do is minus 5, which means that is what, that's how I'm going to end my, my recursive formula. Okay, so there's two parts here. Tell me the first term, and then from the first term, tell me how to get to the next term, and so on and so forth. And that's where this minus 5 comes in. And this isn't a coincidence that this is that common difference. So if the pattern was adding 5 every time, I would change what's in yellow to plus 5, basically. Okay. And then the explicit formula we worked on in 9.1, we're going to treat this a little bit differently. And the explanation is going to take a little bit of time, but I think you'll understand why we write it the way we do. So if you think about the second term here, okay, the second term, which is 18, we got from 23, which is the first term, we subtracted 5. Then if you think about the third term is 13. Okay. The third term we got from 23, we subtracted 5, and then we subtracted 5 again. The fourth term was 8, which we got from 23, subtract 5, subtract 5, subtract 5, because we minus 5 3 times. And by now you might kind of see where we're going with this. To get the fifth term, I'm going to take 23 and subtract 5 how many times? To get the fifth term, I'm going to take the first term. Okay, if we look here, I'm going to take the first term and I'm going to subtract 5 1, 2, 3, 4 different times. Okay, so from the first term, I'm going to subtract 5 4 different times, but a shortcut for that is I can just do minus 5 times 4, which allows me to stop writing minus 5, minus 5, minus 5, minus 5. So then if you can imagine the relationship between this number and this number, to get the sixth term, I'm going to take 23 and minus 5 times. Let's say I wanted the 10th term, I would take 23 and I'd minus 5 9 times. To get the 100th term, and by now you're probably already fast forwarded this, so maybe you're not even hearing what I'm saying. I'm just talking to the internet. But then here's what we want. Here's the reason that we do all that. To get any term in this sequence, it doesn't matter what term it is. Okay, you pick a number and we can find it right away. It's very simple. I'm just going to take 23 and I'm going to subtract 5 n minus 1 times. Okay, so again, if you look at, to find the 100th term, we subtracted 5 99 times. To find the 10th term, we subtracted 5 9 times. So to find whatever term number you want, we are going to subtract 5 1 fewer than that number. So we use n minus 1. This is the explicit formula. Okay, so I'm going to take this, see how good my notability skills are. Copy. We'll come back up here. So the explicit formula is fixed. Okay. There's our explicit formula, and that's how we're going to write it. Okay. So we have the recursive formula on the left, the explicit formula there on the right. In general, this is how every explicit and recursive formula will look if you have, if it's arithmetic, if you know the pattern is adding or subtracting the same every time. Okay, so recursive will be insert the first term, so a1 equals 10, a sub 1 equals 20, whatever. And then again, this will always be the same. A sub n equals a sub n minus 1, and then you just add whatever the common difference is, plus 5 minus 3. And then notice for this, we have the explicit that we just wrote was a sub n equals 23, because that was the first term, minus 5, which was our common difference, and then we always multiply by n minus 1. Okay, so the first term is right there, and then the common difference, which we call d, is right there. In this case, we're going down 5, so that's why it's minus 5. Yeah, so those are, I mean, that's basically it. And now the rest of this lesson is just like, how do we use it? And so we'll try and go through this quickly. What is the 100th term of the sequence that starts 11, 17, 23, and so on? So let's look at this sequence quick. We need to first identify the pattern. From 11 to 17 is adding by 6. Sure enough, that's the same thing from 17 to 23. Normally you need more than just like two, normally you have more than 3 numbers just to find the pattern, but here we see it's adding 6 both times. So we can write the formula to find any term. You're going to start at 11 and you're going to add 6 n minus 1 times. Okay, so if I want to find the 100th term, which is what this is asking for, I believe, 100th term, I'm going to take 11 and I'm going to add 6 99 times. It's always 1 fewer. Okay. Now, in the calculator, that's going to look like 11 plus, and then the calculator, because of PEMDAS, will do 6 times 99, which is 594. And then add 11 to that, and we get 605. This is our 100th term of that sequence. So it's pretty powerful stuff, considering that we only were given the first 3 numbers. In about 45 seconds, we were able to get the 100th number overall. Same sort of thing. What is the 100th term of the sequence where a sub 1 is 12 and a sub 4 is 7.5? So if you think about what that means, a sub 1 means the first term, the first term is 12. I don't know the second, I don't know the third, but I know the fourth is 7.5. Question is, what's the 100th term? Okay. So I really actually don't care about the second and third terms. So what I'm going to do is, again, I'm going to treat this kind of like slope. The first term is 12, and the fourth term is 7.5. So I'm going to go ahead and set up my slope equation, which is the second number, y2 is what we call it. y2 minus y1 over x2 minus x1. This is not the only way to find slope, but it's one way. That ends up being negative 4.5 over 3. If I divide those, I get negative 1.5. This is my common difference, which means the pattern is I'm going to subtract 1.5 to get from term to term to term. So if I cared about the second and third term, I could find it very quickly by just subtracting 1.5. I don't care about what the second or third term is. So I'm going to go ahead and take this, and this is all fine and dandy, but I'm going to put this to the side for now. I'm going to go ahead and write that explicit formula using what I now know. Okay. So I know that I started at 12. So to find any term, I'm going to start at 12. I'm going to subtract 1.5 and minus 1 times. In this case, again, I'm finding the 100th term, so I'm going to subtract 1.5 99 times. The nice thing about our graphing calculators is you can just type this in. So 12 minus 1.5 parentheses 99, and we get our 100th term of negative 136.5. So A sub 100 equals negative 136.5. Pretty powerful stuff to be able to use that explicit formula. Again, the recursive isn't helpful all that often, at least for these easier sequences. Later on, when we get to some of the crazier sequences, it makes a little bit more sense. So go ahead, pause this if you want, and see if you can find the 73rd term of this sequence. First term is 712, and sixth term is 797. So first term is 712. The sixth term is 797. So again, going to set up essentially what equates to a slope equation. 797 minus 712 divided by 6 minus 1. Okay. So here I subtract the tops. What's that? 85 divided by 5, and that equals 17. So that means my common difference is positive 17, telling me that I'm increasing by 17 every term. So how we're going to use that now is to find the 73rd term. So to find 73rd, I'm going to take the first term, which is 712, and I'm going to add 17 to that 72 times. Again, always one fewer than n. So A sub 73 is equal to 712. I'm not sure why I'm writing this again. I'm going to go to the calculator. 712 plus 17 times 72. And that gives me my 1,936. 1936. There's our 73rd term. Okay. So again, we can use this slope type look only because it's arithmetic and it's adding the same amount every time. In 9.3, when we get into geometric, that's not the case anymore. Okay, so to wrap this up, at some concert venues, the rows are curved, which allows more people to be close to the performers. At most of these venues, the front row has fewer seats than the rows further back. So if you think about if in an auditorium they had just a bunch of straight lines, right? Here's the stage. You just had a bunch of people sitting like this. By the time you get to the fourth row, you're actually pretty far away from the performers. So obviously, as you've seen in every auditorium, you have something that looks like this. So the distance between the audience and the performers is everybody's a little bit closer, right? Because they're kind of making a circle. But because of that, the front row is going to have fewer seats than the rows in the back because there's just not as much space. Assuming each row, so this is assuming each row has 3 seats more than the row in front of it. How many seats does the front row have in an auditorium with 37 seats in the 12th row? So this is saying in the 12th row, we have 37 seats. And the question is, how many seats are in row number 1? Okay. Well, in row number 1, that is 11 rows further up. And there would be more information here that I need, right? But we know that in order to get the 12th term in a sequence, you're going to take the first term and add the common difference 11 times. So let's just fill in what we know. We know the 12th term is 37. We don't know the first term, but we do know that the common difference, or the change between each row, is a positive 3. So as you go up in row number, so as you go to the second, the third, the fourth row, we are adding chairs onto that. So this is plus 3 times 11, and now we can just solve this linear equation for a sub 1. So this is a1 plus 33. I subtract 33 from both sides. I get that a sub 1 is equal to 4, meaning that there are 4 seats in the front row. 4 seats in row 1. So there's a couple different ways that we can use arithmetic sequences to be able to answer some questions, both word type problems and things that aren't word problems. So the homework for 9.2 is page 575, 7 to 43. Gonna peace out.